Okay, so moving from a univariate to a multivariate regression setting isn't that difficult. The tough part comes when you start interpreting the obtained results. So, let's go through this process together. Running a multivariate regression. We will use the same housing data we used for the univariate regression we ran earlier. Two things should be done before enlarging your set of independent variables. First, write down the names of the columns corresponding to the explanatory variables you would like in your regression. Let's suppose the two variables we would like to add are number of rooms and year of construction. Our goal is to see if they affect the price level of houses. The second point we want to make reflects an important part of the Pythonic syntax. I hope you thought about it. We must double the brackets around the names of the independent variables to show x will be multidimensional. Alright, now, with the help of the same lines of code, we will run an OLS regression. Let's examine the values of the statistics obtained. The coefficient of the constant came out in scientific notation. After we transform it to a standard notation, we will get a result near 452,000. So, the coefficient values of the constant and of the house size drastically changed. Do you agree? The constant jumped from 260,800 to 452,000, while the house size beta dropped from 402 to 341. Does it seem that by adding the other two independent variables, we destroyed the nice results of our univariate regression, and that house size cannot explain the house price anymore? Please do not rush to make such a conclusion. Let's check the R-squared value of this regression. It changed from 0.678 to 0.736. Therefore, according to this statistic, the second model is slightly better in terms of explanatory power. So, at least some of the independent variables influence the price of a house. The coefficient p-values are an important indicator we should consider. They are not small enough, being greater than 5%. This means the three coefficients are not statistically significant. So, what should we infer from our analysis? Is house size a good predictor? What do you think? An experienced researcher runs hundreds of regressions before making a sound inference. For instance, now we can run 3 other regressions with 2 independent variables. Size and number of rooms could be the explanatory variables for the first regression. Size and year of construction for the second one, and number of rooms and year of construction for the third one. When we skim through the p-values in the new output, we can see year of construction does not get a low p-value in any of the 2 regressions it has been involved in. This means it is not related to house prices. In these same regressions, the p-value for number of rooms and house size is practically 0, which is amazing. When we run a regression with only these 2 variables, size and number of rooms, their p-values increase significantly. So, we cannot confirm they can influence the price of a house. At this stage, even if we cannot make a firm conclusion, these results can give us good guidance for future research, and this is a valuable asset. What could we do next? First, our output suggests that if we gather more data about more observations, house size or number of rooms might prove to be good indicators of house prices, and their p-value will probably decrease in the regressions we will run. How come? Well, in our calculations, the value of the R-squared was high. This gives us confidence that in general, we have gathered a good set of explanatory variables, so it might not be necessary to change the set. In addition, there could be a problem among these 3 explanatory variables. Most probably, house size and number of rooms are related, and they act as a single explanatory variable. This means they are the same factor. We should gather data about other types of explanatory variables. What type of people are the neighbors? What is the distance between the house and downtown? Are there any supermarkets close by? All these might affect a house price, and they might change the coefficients of the variables we used so far. If they don't, and, for instance, house size turns out to be always significant for the explanation of the price level, regardless of the number of other explanatory variables we include in the regressions, then we might easily infer house size definitely helps us explain house prices. It would be great if we could manage to do that. So, does it make any sense to run regressions? At first sight, it seems we will never obtain the right answer unless we run a lot. In addition, good data is not always available. But please don't fear that. Regressions can give us a good direction for future research. Following such a direction could help us assess whether a certain factor influences the phenomenon we are trying to explain. Furthermore, regression analysis can be invaluable when we study the past to understand the future behavior of financial assets like stocks. This will be the main topic of the next section of the course. See you there!